And I guess the first thing that I want to do is to just go over a few points about the fact that this is a prototype video. It's about actually the act of prototyping as it is about building a current clamp. Now, I'm going to pop a little bit of stuff in here just to manage expectations a bit. So in video 2, I did say I don't think this will be the last build. There'll have to be another iteration. And that will be the case, as we shall see. So why are we prototyping and not just kind of calling this a build? Well, there are lots of reasons for prototyping. Now, enthusiasts often really mean by prototyping that they just build one, sketch it out, maybe do a little bit of simulation or something like that, pop it together and sort out anything that doesn't work. And so that's your prototype, and then if you build another one, that would be your production model. But it's all about uncertainty. How uncertain are we in what we're making? How much of it have we done before? So, so for example, I've used op amps quite a lot before, so I'm not really worried about that. Never used a Hall effect sensor in my life. Our first type of prototyping is we just expect it to sort of work and we're just going to fix it. The second type is there are actually parts of the system that we're building that we're completely comfortable with and we're happy to build, and maybe we're reusing circuits that we've used before, but there are a few bits that are new to us that are novel and interesting and we're not quite sure about, and we need to just deal with those bits. So that would be like a partial prototype. We might just make things in modules and prototype just the missing module, just the difficult bit. The third one is where there's lots of uncertainty. So we're setting out on something that's fairly new, and that's what we've actually done in this case, and that's the third or fourth bullet point on the slide. And this is where we're actually going to kind of deal with the uncertainty by doing lots of sort of incremental pieces of work and building up to hopefully our final product. So in this case, we first of all had some simplifications. So one of the things that was worrying was, for example, the zeroing circuit. You could spend a lot of time getting your zeroing. So we know that we have to zero a current clamp, and you could spend a lot of time fine-tuning that zeroing circuit. That's in the way of getting the basics working. So we don't do that. We kind of just move it out of the way and start thinking about a simple zeroing circuit that's probably not up to the job, but will hopefully do well enough to enable us to move forward. Because one of the earliest things that we have to decide is, do we even want to keep building this? The next step, of course, is simulations, and I did some simulations, and we saw some of that in, I think, video 1. I did some 3D modelling. That seemed to be alright. Built some early versions of that. They weren't alright, had to build some more. Did some breadboarding. So we built this on breadboard. We found there's a thermal problem. We go back, we redesign that bit, and so on. So you can see the kind of incremental steps, just kind of doing a little bit, sorting out a problem, do a little bit, sort another problem, work it in little separate sections, keep going, and then we get to our first build, which is really what we're going to look at in this video today. We're going to assemble all the parts and just see what we think about how far we've got, and then we'll evaluate it and think about any modifications, and then finally we'll come to some conclusion. Is it good enough? Are we just going to make it? Are we going to abandon it because actually we've set off on a bad route, or is there a bit of a rethink needed? So, quick review of the current clamp itself. This is supposed to be a low-cost current clamp, sort of a tenner, something like that. AC and DC, and it's going to use a Hall effect sensor to do the DC. I was thinking I might do it in a DIY kit, and part of the reason for prototyping was seeing how that might work out. I kind of had it as a sort of, thinking about like old Airfix models or aeroplane models and things like that used to come on a sort of flat plane with all the parts injection molded. Because of the volume of manufacture and things like that, that isn't sensible at all. We found that out during the prototyping. We've got a case to make. It's a complex case. We've got a PCB that we need to do, which has to just fit inside that case. We want the soldering to be suitable for beginners. We want it to be very small. We want the resolution to be really high, or the precision to be really high, 1 millivolt per milliamp. Now that's 10 times higher than most of the low-cost clamps that you can buy today. So there's probably a reason why they don't do 1 millivolt per milliamp. We'll find out. We want the parts to be easily available, and I do actually want to have a ready assembled PCB by my manufacturer. Some of the problems, I mentioned the zeroing earlier. One of the problems for me is the plastic case. It's a complex clamp. It's in multiple parts. It has to clip together. It's got hinges, springs. It has to house ferrite beads, sensors, PCBs, cable reliefs, and all sorts of stuff have to happen in that case. Now, I'm quite used to cases, you know, boxes, drill holes in them, stick things in them and things like that. That's not really a big problem, even a few custom cases. But this one is a pretty different magnitude. It's not the stuff I'm used to working with. So prototyping is how we hopefully deal with that. I haven't done Hall effect sensor stuff before. What problems am I going to have with noise? I kind of think noise is going to be a problem. I think the Earth's magnetic field is going to be a problem. The zeroing circuit will have to deal with that ultimately, and the simplistic one that we're dealing with at the moment isn't going to. What about the bandwidth? I'm aiming at 20 kilohertz bandwidth. Will I get anywhere close to that? What about the ferrite itself? You know, how do I even get the ferrites I want? How do I manage the fact that I need a gap in the ferrite for the sensor to sit into? You know, there's a few options there. How am I going to hold it in place? And you know, this sensitivity, what sort of problems am I going to have from that? So anyway, let's go and actually have a look at what the produced PCBs and things like that are actually like. Okay, in the spirit of full disclosure, I thought I'd show a couple of the failures along the way. So this is the mechanical side. This is version 1 was a bit of a bust. I had to go back and redesign that straight away. So here is version 2 with an integral hinge and quite a nice box section. And you probably can't see it on here, but there's kind of like a lip type arrangement for the lid to fit into. And here is the lid, and it clips into place. So far, so good. However, build-wise, this has caused a few problems. It's splayed out of the top. Where the build supports have been, it's just a very bad finish. This is just way too flexible and doesn't fit very well. And the reason that it doesn't fit very well is because, again, this also has support problems along the edges. This front corner has also distorted, so that's no good at all. This is the top lever that kind of fits on and kind of springs like that. There's just 2 pins that go into the hinge. And that's pretty good, strong enough just. And yeah, it pivots okay. It's got the spring mounting point on it and all that sort of stuff. So that's pretty decent. Again, it's got some finishing problems where the supports have been. But overall, yeah, that's not a bad first attempt. Well, second attempt. So anyway, back to the drawing board on that. So these sides here are so weak they've actually splayed out. So I've changed the design there. So instead of being like an L shape, kind of one has a kind of step on it and the other has the opposite step. I've actually gone for a different design where hopefully I can get this apart. So this is the part that holds the PCB, and we can see that structurally it's a lot thicker. This is a 3mm wall, 2.8 or something like that actually, but and it has a groove cut into it, and there's a groove on the end and so on, and it has some supports for the PCB and what have you. It's got a whole lot of stuff going on there, in fact, and some divots here into which the hinge is fastened. Now it's flat bottomed, it doesn't have the hinge molded as part of it. Now I might change that, because I did that because I wanted to put this side on the build plate, but doing that has caused a problem in so much as I've lost all of my radiuses on the edges. This gap has closed up a little bit and things like that, and it's got a little bit of a rim around it. So dimensionally it's correct. Finish wise, that's a bit iffy. The hinge has been modified so it can be built easier with less supports, but essentially it's just a little hinge. It has these pins which go into the kind of hinge and lock everything in place. So they're a very tight fit and they don't come out again. Well, you can kind of pull them out, but you'll wreck them and then you have to put new ones in. The top part of the pivot is now, of course, very nice indeed. Here's one assembled. So yeah, that's working very nicely. It's very strong. This is made in like a ABS type material. Here's the pins in place to act on the pivot. I haven't put the spring in this, but that's fine. I'm going to spring to fit. And here's the bottom section all assembled. So you can see that that's significantly better. It's very strong. There's no problem with it at all. Here's the second half of the bottom. So whereas the bottom was done in one sort of deep trough before, it's now split down the centre, and it has all things like little clips and things to hold it on. So this is kind of nearly there. It's just not perfect. I mean, it's probably never going to be perfect, but it's just not good enough at the moment. It's nearly good enough. So for example, obviously in order to go into those slots that I showed you, we've got little tongs that stick out here. Now I did leave a little bit of clearance on there, but it turned out to be fractionally too small. And although this one is assembled, I kind of had to clamp this in order to get it to close up. There's also a fault on, there should be 4 of these pins going around the edge, and there's a fault on one of them. It hasn't got enough physical support to enable it to, these spring fine. I'll do that. You see they kind of spring in and out, they're fine. And I can do that multiple times. I'm saying on this one at the back here, and there should be another one just here, but it's snapped off, and that's because it hasn't got enough support material, so I need to do a modification for that. And for the whole lot, I need to do some modifications on how I actually do the build, because it shouldn't have this somewhat flat yellowed hard bit on the back. That's caused by the fact that the first few layers on the print have to be cured for longer, and so you end up with a thicker sort of overflow on either end, and yeah, it's not quite what's intended. Anyway, we are 99% there now, so I just need to move on to version 4 and adjust out all the little niggles. Okay, so the PCBs have come back fully assembled from the manufacturer. Okay, there you go. So I have to manufacture 10 of them. They're just taped together on the back, and they are actually separate circuit boards. Let's just separate one off, have a little look at it. As you can see, it's pretty much surface mount all the way, and the components chosen are chosen because my supplier can provide them. This is made by JLC PCB. Yeah, I think they've done a pretty decent job over it. It's a 2-layer board. You can see it's got some quite big earth planes on it, things like that. Yeah, and obviously I've had them do the surface mount and reflow, etc. for me. So there's a couple of connectors, a connector here for the power and a connector here for the actual coax cable that aren't connected. And on the other end are the 3 pinholes for the sensor. So other than that, it's fully assembled. These 2 holes are not in fact screw holes, although you could use them for that. They are actually little mounting holes that will hopefully line up with 2 little mounting lugs in the case. So I'm thinking of making a kit for these. So I'll provide this board and some case components and things like that, and people can assemble their own. Now that raises a lot of questions. I've never developed a kit before. How are the tolerances on these boards? So I can see, for example, on the side of this board, there's a routing point there where they've left them connected together until the end, and the same on this side. Will it actually even fit in the case? Who knows? Maybe I'll have to alter the case design to deal with that. Is this output position okay when it comes to assembly? How easy will it be to put this together? So let's just have a look at a couple of the other bits and pieces. So here are all the pieces for the current clamp prototype. So I'm not expecting that out of this will come a perfect, I'm completely happy with it current clamp. I'm expecting that what will come out of this is a series of lessons that will then be applied to make a better current clamp. So we've got the circuit board here, so I'm happy with that in principle. It's been through a couple of iterations of circuit design on breadboard. So first of all, I simulated it. It looked okay. I put it onto the breadboard, but I'd taken a few shortcuts to keep the costs down. And when I put it onto the breadboard, it wasn't thermally stable. So I've come back, I've altered this. There's a voltage regulator on here that didn't used to be on here. Higher quality trimmers, various bits and pieces like that. So all being well, this should now be pretty thermally stable. And fingers crossed also, these trimmers will line up with these holes, because that's the intention, to be able to trim these with this in its case through those little holes. Someone has mentioned on the comments about this and has asked really whether or not these will be accessible, and yes they are, but also sort of said, you know, why don't you put a digital circuit in here so that it can sample the offset, and because that's what one of these trimmers is for, to zero it, because obviously in different environments the zero will need to be adjusted, and that's entirely true. The reason I haven't done it is because this is a simple prototype. I want to get the basics in place and right before I move on to the complexity. Now, His suggestion was that we sample that digitally and then we output a digital offset, and that is entirely possible. However, this is a very, very wide dynamic range device. So that means we need a wide dynamic range ADC and DAC, and that adds to the cost and starts making the microcontroller quite expensive because we need a lot of bits in order to get the precision to make this work. So a different solution to that is to use an analog sample and hold circuit. So you just press a little button for a couple of seconds, it zeros, holds that, and then you can make your measurements. So, but you know, that would detract from the core circuit. This is a prototype. Don't want complexity and things like that detracting from the core circuit. This is an amplifier, an offset adjustment, a second amplifier, a regulator, and this is a voltage divider that creates a plus minus 6 volt supply. And that's it. That's all that's on that board. Don't want any more complexity than that. Thank you very much. In terms of the case, the aim is to produce this as a kit that people can assemble. So somehow the two pieces have to come together sensibly. I've had a lot of difficulty with that, the mechanical side, and additive manufacture is certainly not my thing. This is iteration 5 of the shell. It's not ABS, but it's an ABS-like resin that it's made out of, and it's very, very strong indeed. So I'm not worried about that. That part is solved. The manufacture and repeatable manufacture is, however, still a little bit up for question. Okay, let's try and get this assembled, see what happens. So first up, I need to hopefully get one of these ferrites into here. I'm not too worried if I end up having to glue this, but I was hoping that it would clip into place. And we're not quite there at the moment. And I need to find something to just push it in with. Oh, there we go. Okay, so that is that ferrite. And that has fitted very nicely. I'm happy with that, I think. So I'm pretty happy with that ferrite. That's gone in quite nicely. And we can see the point where the sensor will just rest on that ferrite. Next then, we've got to prepare the PCB to go into this. So these are hopefully going to fit. They're from a company called CUI Devices. So, okay, thinking about prototyping, my first impression with this is it's interesting. This actual connector does twist more than I expected. Now, the next question is what to do with this, which is the cable connection. And this, the square one is the actual signal output, and the round one is the ground. And I need to just decide whether I'm going to put a socket on that or not. One of the questions I want to answer is whether or not I want to leave this here. This socket could be moved right up here where this hole is at the moment, and the hole can just be moved along a little bit. At the moment, getting my feeling is I want to do that. This is really near the out, and if it was over here and I reshuffled these a little bit, then I would have enough space to put a little push fit connector on there, like a micro one, admittedly, but there would be enough room for it. So yeah, I think in future that will move. Let's find a little bit of cable, or a pre-made cable might be even better. Okay, so yeah, that definitely confirms that it would be far better to relocate this right down this end and put a little socket on for that purpose. That was a pain in the bum to solder, and I'm still not entirely certain that I'm actually going to get that successfully out the case. So yeah, so that definitely answers that question. So far we've really kind of learned that we want to move this down, and it doesn't solder very easily. We've learned that there is a bit of twist that applies on this socket when it's soldered in place. This, I mean, it will go out the case, but no strain relief. I mean, this would be better if it had the strain relief molded on. I've just used a couple of pieces of heat shrink for that, which are probably going to get in the way, but anyway, we'll see. The idea is that now we place this in the case, it magically fits, one hopes, and that we then form the first of the sensors. Having done that, we can then make a little jig in plastic that can be supplied along with this to enable the sensor to be bent in the right place. But anyway, first jobs first, let's see if this even fits in the case. And it should go in and it should clip into place. That is the plan. And something appears to be stopping it sitting down neatly. Not quite sure what. Ah, there it is, it's in. Yep, okay, so that has gone in, it has clipped in the intended way. So there are little holes just here and here to take location lugs, and over here there is a clip. The back is located correctly by this actual socket fitting into its position, and in theory by this cable also fitting into its position. So now let's have a look at the other side and make sure we can see the holes for the sensor, which we can. And I have to remember which way this blinking sensor goes in now. So Hall effect sensors, thank you very much. Okay, so I've got a little diagram, VCC ground out with the sort of chevron slopey bit at the front. And here's the board. This is the top view of the board. Out would sit that way. However, the board is upside down. So sense, as I look at it, is going to be nearest me. So I need to fit it in this orientation and get everything right. So I'm just going to have to eyeball this for this particular bend, I think. And then we can hopefully use that to create a bending jig in the future. Back to why do we prototype? That's 2.6 millimeters. Okay, 3 millimeters appears to be the point at which we need to bend it. As I said before, I think, you know, a lot of the purpose of prototyping this is to see not just how do we build it, but how do we build it so that people can actually put it together using a kit. And right here we have an example of the problem. As we bend these pins, they actually close up a little bit. It's really, really tricky. To get them in the holes. Hurrah! We're in. Okay. So I'm just going to attach a little blob of blue tack on the back here just for a second to hold it in place while I solder it. Whew. So okay, so that kind of highlights a problem there, I think, that's going to need to be dealt with. I'm also trying to assemble this with things like the size of soldering iron tip that people might actually use. Okay, now this, again, back to why we do the prototyping. So if we look here, this centre pin here is the ground, and it goes up to here, and we can see that there's ground plane around here, and up to that hole there, which is a SMD hole that the manufacturers put in so that they can mount it in a jig. However, this is the plus on this side, and it is perilously close, in fact, to the ground plane. Well, it's hard to tell, in fact, whether I might have even short-circuited it while I was soldering, because it is so close. Okay, so we've fitted the DC jack, we've fitted the cable, we've fitted the sensor, we've got the ferrite bead press fitted into place. I'm sort of okay with that. It's just not quite as smooth as I would like. I think there's just a little bit of clearance extra needed in the case. So I've made a little note of the things that we've learnt so far. So first of all, I said that the DC jockey tends to, that socket tends to skew a little bit. And that just means I should put a bit more clearance around that. The cable, I'm really not happy with that mounting method. So I'm going to put over here, I'm going to put something like maybe an SMB. Let's see if I can find something even smaller than SMB to put in there that will go onto this cable size. This is a 2.5mm diameter cable. We could do with just a teensy bit more clearance for the PCB in the case because of the leftover edges from the routing, where they've actually kept the boards together as they've manufactured them. The little sticky outy bits are getting in the way of the case. So that we need a spacer jig for this piece, the sensor. So 2 points for that. One, so we get the bend in the right place, and secondly, so it'll actually space it off the board. So the design can be, I've put the ferrite in first and then fitted the sensor to fit. What we really want to do is to solder the sensor onto the board with a plastic spacer so that everything ends up in exactly the right position, put the board in and then pop the ferrite in afterwards. It will still lift out because it will lift out from this end here. I need to pull back this ground and yeah, and there's a 3mm bend on that. So that's great. Okay, let's see then if this guy will fit. Now, I'm not really 100% confident about this, to be perfectly honest, but we'll give it a go. Now, I did, in version 4, have to make a few adjustments because it was too tight a fit. And truthfully, it feels like it's too tight a fit all over again. The ferrite itself has moved. That's not good. Yeah, so we've actually still got the same problem that I had in prototype 4, whereby the case was actually, the case has got like a tongue and groove around it, and the tongue and groove was actually too tight. Wasn't enough clearance on it, and as a result, the case wouldn't fit together perfectly. And we kind of got the same problem again here. The tongue and groove is still too tight, so I'm having to kind of lever it in. And it's not kind of clipping into place as I would hope. So it's kind of there, but not quite. Still more design work to do on this case. There's still more design work to do on the plastic fabrication because, you know, there's a little indent here where I can fit my fingernail and it shouldn't be there. And the same at this end. the plastic has curved back and isn't really quite as good as it should be. On the positive side, looking at here, there are my two trimmers, exactly the right position, so that worked at least something worked. So again, slightly more clearance required on those holes, so I'll just make a note of that. So for the purposes of this one, I'm just going to use a quick super glue. However, I do think that this is actually moldable as one piece now, because things didn't quite go as I expected. So this is intended to have a little bit more clearance than it has. I think it is going to go in, but it's meant to actually be quite a loose fit in this one, because the intention was to put like a low modular silicone behind it to hold it in, and that would actually act almost like a spring to push it forward. But anyway, there it is, it's in, and it's a push fit. Okay, fair enough. Now the other thing I'm pretty sure I have problems with is these pins. So these are intended to go through this hole and kind of latch it in place. Now they should be the right length now. I should be able to get them in from opposite sides, because I had actually manufactured them slightly too long on the previous iteration. But I think they've still got a problem, which is that they don't actually snuggle into the hole. So there's a recess here, which is about half a millimeter deep, and the head of this is actually supposed to go into that, and it's not doing so. And the reason it's not doing so is because of the manufacturing method. So this is built on a build plate, and that face just there sits on the build plate. Now the first layers of the resin get extra exposure, so they stick to the build plate tightly. But what that does is it causes the light to diffuse around it a little bit, the ultraviolet light that sets the resin, and widens the component at that point. Now I had compensated for that, but not enough, evidently. What am I looking for? Spring. Now earlier, notice I had a spring. Hopefully this will be the right size. Now it looks quite a large spring for this job, but the reason is that when this is actually in position, pliers, come on, I'm losing everything today. Oh, that one's in. Excellent. Let's try and get this one in now. So clearly I've manufactured this bit a bit too tight. That one's in as well. Excellent. Right, okay, we're in. Whew. Okay, so after a bit of faffing, here it is, the first one assembled. Now the only thing that hasn't been included in this prototype is the actual cable relief gland on the back of this cable. But other than that, this should be a fully functional prototype. What do I think about it so far before testing? I'm mixed, I'm a little bit mixed. I think the plastic moulding has proven to be extremely difficult, perhaps just because I'm not used to it. It is 85 millimeters long, so that is just over 3 inches. It's 17 millimeters wide. It closes up fine, its height's fine. It's got a 5 millimeter cable hole, that's all right. That's what I was looking for. So overall, it kind of works okay. The clamp mechanism works okay. The ferrite sitting position okay, even though they don't have that springiness that I was expecting to put in there. They've actually worked out really well, so I'm very happy about those. the case, quality of the case, I find a bit lacking, to be perfectly honest. It's got a bigger gap. Yeah, there's a bit more work needed on the case still. So we'll be on iteration 6 of the plastic case. But in terms of its overall design, it is about there. It works as a current clamp. So let's give this a go and see how it is electrically. Okay, so we've assembled the clamp. So I've had a look at the circuit diagram, which isn't really going to show very well, unfortunately, on here. There we go, I'll try like that. There we go, circuit diagram. And I think that the gain works in an anti-clockwise direction and the zero should be almost fully clockwise, I think, in order to get round about 0 volts. So you can see we've got some voltage on the meter here. This one's connected to the output. There's a little bit of voltage going on there. Now if I turn the gain anti-clockwise, then that is going to move quite a lot. Now unfortunately this is clearly magnetic and affecting things quite a lot. Okay, it looks like the tip isn't, so that's so yeah, I don't know what sort of gain I've got on there. We've got some sort of output. Will it 0 or not? The answer is yes. I can adjust its 0 point, although it is really, really sensitive. So clockwise is lowering the offset, but by goodness, that is sensitive. I'm going to kind of leave it at that for the minute. Oh. But you see there's definitely some sort of noise on here, and I think that's just going to be some pickup and some filtering problems and things like that. So yeah, we want this to work with both AC and DC, so that's hard to deal with. So I suppose the next question is, do we have any sensitivity to magnetism? And the answer is absolutely we do. Take a look at that. So as I bring the magnet in, there we go with 4.5. That's clipping out at 4.5 because we've got a 606 volt supply. So actually, it would appear this clamp is working. Oops, that's just turned itself off. Thanks for that. Let's just have a look at some calibration now then. Okay, so this is just a positive wire coming out my power supply and going off to my programmable load. Now there's a little bit of a problem because this case has become a little bit brittle. Since I filmed this segment and the previous segment, it's there's a little bit of a time gap. So I do just kind of need to keep this. So it's become a bit brittle, and the hinge has cracked a little bit. So yeah, I do kind of just need to deal with that. Now we can also see that as I turn this, that the kind of zero changes quite a lot, unfortunately. So you know, we could put it in any angle we want, but we'd have to re-zero it all the time. If I put it upright like that, which is what I'm going to do, I think, just so I've got a nice stable surface, then we can see that that's now at 186. So clockwise I said was lower, didn't I think? Whoops. Okay, so there we go. I'm going to leave it at that as near enough, and what I'll do is I'll press rel on here just to zero it, and we'll turn on the programmable load, and we'll turn on the power supply. The power supply is set at 12 volts roundabout. and it's set to deliver 100 milliamps. Now we're not done too bad here, 88. Let's turn it off, and we're down to sort of, let's turn the valve off again for a second. Yeah, 85, 82, something like that. So if we increase the gain, so there we go, we've got our roughly 100 milliamps, or actually minus 100, but I don't care about that. Turn it off, pretty much zero, so we're fractioning it over since we're going negative. Let's try 1 amp then on the programmable load. Turn the power on, and there you go, 1.05, so that is pretty damn decent. Let's just trim that down a bit. So now we're within about 2%. Okay, we're better than 1% at that. So I'm pretty happy with that overall. I mean, it's a bit noisy, and it's clearly very susceptible to moving around and often has to be zeroed. I suppose the long and short of this is I'm going for 1 millivolt per milliamp, and all the commercial ones are going for 1 millivolt per 10 milliamps, which actually would mean that they're reading that. They look nice and stable and perfect. Mine has that extra digit, and that's what's causing me the problem with the noise. There you go, there's my 1 amp. Let's try 2 amps. And there we go, 2 amps. So yeah, absolutely spot on. That's a nice linear response. It's doing its job, but there are clearly some constructional and design issues to be dealt with. So I think this is usable, but there are some things that we do need to deal with, and I'm just going to finish up the video by taking a look at that. So now that I've looked at it with DC performance, I wanted to take a moment or two and just have a look at some of the AC stuff using the scope, and ran into a bit of a problem. So this yellow line here, which is basically noise or some form of interference, is really masking whatever signal I can input. Now I can just about get enough to make that wiggle around, but only at fairly high currents. That's measuring like the equivalent of an amp backwards and forwards on there, maybe a bit more. And that's not really very good, because that makes it extremely difficult to see anything. And although we could put some high frequency filtering on that, which is essentially what's happening when it's plugged into the multimeter. Yeah, so the multimeter is working, but that's perhaps the source of its instability is all this noise. So where's this noise coming from? Now my immediate thought was, oh, I've built an unstable op-amp circuit, and since it's going into a 1 meg input on here, it's seeing its capacitive and it's all unstable, and so I've terminated with 50 ohms. It's obviously it's reduced in magnitude slightly, but basically it's still unstable, and that was kind of my first thought. Now I do actually have, if this will focus, well, it's not going to focus. I do have a capacitor to remove any high frequency instability installed in the circuit. I've got no reason to think that that wouldn't work, and in fact, as we'll see, it is actually working to some degree. So where is this coming from? Where is that signal coming from? So if I look at, for example, this capacitor with channel 2, we can see there's a huge amount of noise on that. Now capacitor 2 is set to 50 millivolts. If I look at the input, the first input on the op-amp, there's a whole lot of noise. So there's two places that noise could be coming from. One is from the sensor. Now I shouldn't see much of that noise on the sensor because there's a big resistor there. Or it could be coming back through the feedback circuit again, which is a bit unlikely because this is a very small gain on here and there's not a very high frequency going into it. So, you know, let's have a look then at pin 2. That's the feedback. So that is pin 1. There's it. Come on, get in there. That's the output from the stage 1 amplifier. There's the feedback from the stage 1 amplifier. There is the power supply offset to the stage 1 amplifier, and we can see it's got some noise on it, but it's not great. The frequency is different though, so that's helpful. But to some degree we can actually see it does modify the noise signal slightly when we probe it. Let's have a look at the input to the sensor then. And there's the noise right on the input. Now that magnitude of noise is not significantly different than the feedback circuit at all. So we can actually see that noise is present on the sensor. So you have to assume that that is being picked up environmentally, and the combination of that noise plus that high frequency switching on the regulator is causing our problem. Let's have a quick look at the actual power supply as well. The power supply is very noisy also. So I do kind of suspect that I'm picking up noise from all of those different sources. Now this is, the power supply is a switch mode power supply. But there's a lot of noise on that positive rail. But let's just turn that voltage down a little bit, see if we can get it in scale. Yeah, so there's the noise on the switch mode power supply rail. So overall, we've got an awful lot of noise going into this circuit, both in terms of electromagnetism around it and the power supply cable coming in and its little internal regulator creating a little bit of high frequency noise as well. So I'm not going to bother to try and make this work with an AC signal on a scope. We are way off where we need to be for that. Okay, so this was an interesting experience. This was all about prototyping a current clamp or current probe. And overall it works reasonably well for DC, although we do know that there's some instability there and that this is potentially caused by all this noise. So where does that leave us in terms of the probe? It means we've got a circuit that works okay for DC. Its negative side is that the 0 is a bit oversensitive. The thermal problems have gone away, but the angle at which we place this in the Earth's magnetic field does affect it quite significantly. Part of that is because we've gone for a very sensitive circuit with 1 millivolt per milliamp resolution, and so that makes it 10 times more sensitive to the Earth's magnetic field than a commercial one that typically would be the type of thing we might buy off AliExpress or something. In terms of the AC, because we want our bandwidth to be up at the 20 kilohertz, we've got a big problem with our common mode environmental noise, clearly. I did think that this was an instability in the op-amp circuits and things like that, and in actual fact I think that the reason this is a little bit suppressed is because there is a capacitor in the feedback circuit trying to suppress high frequency instabilities. So actually that has helped it a little bit rather than hindered it. Now we could do some more work on that. To use this for AC then, what would we need to do? We would need to put a lot more filtering in it. There would need to be some filtering going in. So this is a little regulator here. We'd need just a little bit more filtering in on there, maybe an inductor, maybe another capacitor. This is a 10 microfarad capacitor here, which is what the manufacturer recommended, but we might be better putting a smaller one in parallel with that as well. We clearly need to do more filtering on the input line here. and possibly do some onboard regulation to help remove the noise coming through the power on this end here. So there's a couple of things that we might need to do there. One is to provide a bit of screening. The other is to actually do some nulling circuitry. So what we would do for that is basically put two sensors in. One sensor in the signal path, one sensor out of the signal path that we want to test, and yeah, essentially null those two off against each other to try and remove some of that environmental noise, and also remove voltage offsets and the impact of the Earth's magnetic field. And we can of course put some high frequency, some low pass filters in there with cut-offs about the 20 kilohertz point. So yeah, there's quite a bit of work to make this work well as an AC circuit. If I could get, if I battery powered this and turned everything off in the lab, then maybe it might work, but that's a bit silly. Okay, so really the purpose of prototyping is to find all this stuff out. There's a great temptation to draw a circuit, shove it into a simulator, see that it works, and go and build it, and then you wonder why it's not so good in practice. And that's why we do prototyping and play around with these things. So I'm going to call it a day on this particular circuit because there's several things I want to do. The other thing on the Zero, by the way, is I talked about doing some nulling using a second sensor. That will remove most of the need for zeroing, although there'll still be a little bit. But I would replace this trimmer-based zeroing with a op-amp based system. So what that would do essentially is you press a button and you would be driving the op-amps to achieve a zero output, so allowing an op-amp to adjust itself, normal feedback circuit really, and storing the voltage that's required to do that in a capacitor. When you release the button, you continue providing that offset to the amplifier circuit, and that's essentially your zero. Now, since the amplifier circuit has an input impedance of about a teraohm, then that capacitive charge lasts for quite a long time. So might just make up that little circuit on its own in a separate video as a little sort of, just a demo as to how to do that. But I think that's certainly what's needed here. That will make it a lot more usable, because we have to just clamp it on a cable, put it in its final position, press that zero button, you get zero, and you just move from there, rather than fiddling around trying to find a little ceramic tool so that you don't affect it magnetically and all the rest of it. Yeah, there we go. Okay, so that's about it. Hopefully you enjoyed that. Hopefully, you got something out of that. If you did, please click the like button, subscribe, all the usual jazz, and I'll see you next time. Take care.